Now we look at the response for RL differentiators. A series RL circuit in which the output voltage is taken across the inductor is known as the RL differentiator in terms of a time response. Although only the response to a single pulse is discussed, it can be extended to repetitive pulses. So we see here below the circuit, an inductor, the output's taken across it, the resistor, and our square wave pulse generator. Initially, before the pulse, there is no current in the circuit. When the input pulse goes from its low level to its high level, the inductor again prevents a sudden change in current. It does, as you know, with an induced voltage equal to and opposite to the input. As a result, the inductor looks like an open, and all of the input voltage appears across it at the instant of the rising edge. So we can see the input is rising. We're seeing the same thing across the inductor. During the pulse, then, the current exponentially builds up. As a result, the inductor voltage decreases. The rate of decrease, as you know, depends on the LR relationship and the time constant. When the falling edge of the input occurs, the inductor reacts to keep the current as is by creating an induced voltage in a direction as indicated by diagram C. This reaction is seen as a sudden negative going transition of the inductor voltage as we see in D. So as you step through these, you can see, like we've seen before, the low to high, the pulse width itself, we see what happens on the output during the pulse width. It's starting to exponentially decay. Then we have the fall here on the falling edge here. The output makes that transition of 10 volts then to a negative, and then it starts to increase here exponentially as it responds to the collapse and the expansion and collapsing of the fields around the inductor. So our output then in D, after one complete pulse, you can see what happens here: rise, decay, rise in the negative direction, and then decay back to zero. Two conditions are possible in C and D. In part C, the complete 5 time constants is greater than the input pulse width, and the output voltage does not have time to decay to zero. In part D, the 5 time constants is less than or equal to the pulse width, and so the output decays to zero before the end of the pulse. In this case, a negative 10 volt transition occurs on the trailing edge. Keep in mind that as far as the input and output waveforms are concerned, the RL integrator and differentiator again perform the same as its RC counterparts. So we can see here again, just like we saw before, where they're going through and they're telling us 5 time constants larger than the pulse width, all the way down to 5 time constants much greater than the pulse width, what happens. So you can see in each case, as the pulse width gets wider and wider, we have a longer decay in both directions, both the negative and the positive. So same example here. If we take a look at L over R, our tau ends up being a time constant of 2 microseconds for this example. We have 10 microseconds as the pulse width, so this is much smaller, and so you can see the waveform here then as the pulse makes its way through the circuit, and we end up then with a 10 microsecond pulse width that matches the input. Okay, so if we again look at the waveform for this one, 2 microseconds. In this case, we're using the exponential value to determine the voltage across the inductor. We have an initial voltage, in this case 25 volts, and then our exponential e to the minus t over tau gives us e to the minus 2.5, and we get 2.05 volts. So we can see here that we end up with the initial 25 volts, it decays down to 2.05, transitions again on the trailing edge, 25 volts, and then comes out as a 10 microsecond decay for our 5 time constants. So the next thing we're going to take a look at is the relationship of the time response to the frequency response. We're going to take a look at our waveform and determine where the high frequency and the low frequency components are evident and characteristic.